Welcome to the video series on the Vermont Green Streets Guide, a resource for planning and building green infrastructure within our communities. In this video, you will hear Becky Tharp lead you through Section 6, the Stormwater Tools.
Section 6 of this guide illustrates ways to design sites to maximize spatial efficiency and create room for potential stormwater practices. Combining this site design philosophy and the full toolbox of stormwater management strategies that are most applicable to conditions in Vermont optimizes the potential for stormwater management in urban conditions. Green stormwater tools can be classified based on their dominant functional mechanism: conveyance and treatment, infiltration or filtration, and evapotranspiration. Understanding the function of stormwater tools can help to prioritize the most appropriate options for your site conditions. Conventional conveyance structures primarily perform the function of moving stormwater from one place to another. The green versions of this functional group differ from conventional conveyance systems because vegetated structures also provide some filtration through plant structure, infiltration as water moves from the surface through the soil profile, and evapotranspiration as plants take up water in the channel. Open vegetated conveyance structures provide more water quality benefit in terms of quantity and quality than closed pipe systems, which solely provide water movement conduits without treatment. Infiltration is the action of water moving vertically through soil media and into the groundwater. This removes pollutants from the water and eliminates excess surface runoff by providing a conduit for water to enter subsurface channels. Infiltration practices are best suited in well-drained soils where stormwater can readily move into the ground. They are most appropriate in areas where there are no hazardous materials either in the soil media or being transported in stormwater runoff. Filtration is a similar mechanism to infiltration initially, but results in a surface discharge of cleaner water, commonly through a piped underdrain system, rather than its infiltration underground. Filtration practices are more flexible in their appropriate application because they do not function by the movement of water throughout a native soil profile and therefore do not require highly infiltrative soils or extreme caution to protect groundwater quality. Green stormwater management tools showcase ways that stormwater can be actively managed. Section 6 of this guide details design parameters and examples for street and parking lot applications for the most common tools for green street application, including vegetated swales, green gutters, rain gardens, also known as bioretention, stormwater curb extensions, pervious paving, stormwater planters, and urban street trees. Each tool description includes how it works and common applications, the environmental, transportation, and community benefits, common constraints, and typical unit cost range. Vegetated swales are long, narrow landscape depressions with slight longitudinal slopes. They are primarily used to convey stormwater runoff on the land's surface while also providing water quality treatment. As water flows through a vegetated swale, it is slowed by the interaction with plants and soil, allowing sediments to settle out. Pollutants are entrapped by vegetation or broken down by microbial action, rendering the water cleaner. Vegetated swales are designed to be shallow, 12 inches or less, with gentle sloping sides, no more than 3-to-1 rise-to-run ratio, to transport runoff only a few inches deep in the bottom of the channel. They can be planted with many types of vegetation, from mown grass to a diverse palette of ground covers, grasses, sedges, rushes, shrubs, and trees. Swales are excellent choices for new residential and commercial development and can be retrofitted along arterial streets and within parking lots where space allows. Parking lots and certain streets that have long, continuous space to support a functioning landscape system are excellent candidate sites for vegetated swales. Existing streets often have a right-of-way space that is underutilized, consider removing existing buried storm sewer pipes and replacing with vegetated swales to achieve a similar conveyance purpose with greater water quality benefit. There are many creative ways to include swales in parking lots. Oversized parking stalls can be shortened to yield a few extra feet for swale installation at the perimeter of the lot. Existing landscaping can readily be integrated into a vegetated swale design with no functional or aesthetic loss. Green gutters are very narrow landscape systems along street frontages that capture and slow stormwater flow. Typically less than 3 feet wide, green gutters resemble planters as they are confined by vertical curbs and have a flat bottom profile. Unlike typical planters, however, green gutters are designed to be flush with the street surface, are very shallow, and perform little or no water retention. While infiltration of stormwater is a possibility, the primary purpose of using green gutters is to filter out pollutants and slow the flow of water using only a narrow strip of landscaping. Like a swale, but possible in highly space-constrained areas where the sloping sides of a swale are not feasible. Green gutters introduce green space along streets that lack landscaping, provide a landscape buffer between vehicular traffic and pedestrians, and create desirable and safe street conditions for people. Green gutters are useful along wide streetscapes as well. In many cases, simply narrowing the travel lanes along a residential or commercial street can yield enough space for green gutter installation. Similarly, for small parking lots, shortening parking stall lengths can provide space at the front of parked cars for a narrow green gutter application around the perimeter of the lot. Green gutters have many active transportation, urban ecology, and neighborhood enhancement benefits. They can act as buffers between sidewalks, bike lanes, and vehicle travel lanes, contributing to the safety and walkability of a street. They're an excellent method for cleaning water prior to entering a downstream water body, and are superior to pipe and gutter systems for this reason. They can minimally help with placemaking and provide community public space. Green gutters typically cost between $8 and $25 per square foot, depending on retrofit conditions or new construction. Common constraints with green gutters include: green gutters require a long, continuous space to effectively slow and filter pollutants. With heavy snow accumulation, it may be difficult for both drivers and snowplow operators to see the width of the green gutter. Adequate markings or grading at the road surface is necessary to overcome this constraint. In steeper topography conditions, green gutters will need frequent check dams in place to slow the movement of water. Rain gardens, also known as bioretention, are shallow vegetated depressions in the landscape. They can be any size or shape and are often molded to fit leftover spaces in parking lots, along street frontages, and in spaces where streets intersect at odd angles. In retrofit conditions, rain gardens can add significant vegetation to spaces that would otherwise be covered by asphalt. Like stormwater planters, they are typically designed to be flat-bottomed without any longitudinal slope to maximize storage potential for stormwater. Rain gardens retain stormwater, attenuating peak flows and reducing overall stormwater volume. They can also allow for infiltration, depending on the capacity of the native soil. Although rain gardens can share certain characteristics with swales, their primary function is to maximize stormwater storage and infiltration, not conveyance to another location. As a result, they are located where they can collect and treat stormwater from adjacent impervious surfaces. Their versatility in size and shape make rain gardens a flexible option for application in space-constrained downtown areas. In well-drained soils, rain gardens can maximize infiltration. However, where infiltration capacity is limited, rain gardens can also be designed as flow-through filtration systems with an underdrain to facilitate drainage in high-flow events. Simple rain garden designs that do not use extensive hardscape or pipe infrastructure can be very cost-effective to install. Rain gardens can be retrofitted in a variety of street applications. Large areas of unused or inefficiently used spaces are prevalent throughout town centers, industrial areas, and residential neighborhoods. These leftover landscape and asphalt spaces are prime candidates for rain gardens to increase stormwater storage and infiltration, as well as green space. Rain gardens are effective in large parking lots, like shopping malls or big box stores, because they can be designed to manage large amounts of stormwater runoff when sized appropriately. For retrofits, several parking stalls can be converted into one large rain garden to capture sheet flow from parking areas. Rain gardens have many active transportation, urban ecology, and neighborhood enhancement benefits. They can allow for separation between sidewalks and vehicular traffic lanes, creating a safer and more walkable environment. They can provide additional stormwater storage and flow reduction, as well as pollutant filtration, which helps prevent damage to downstream water bodies. They can significantly help with placemaking and provide community public space. Rain gardens typically cost between $8 and $50 per square foot, depending on retrofit conditions or new construction, and if the rain garden has landscape side slopes or vertical planter walls. Common constraints with rain gardens include required maintenance similar to perennial gardens, which may be outside the regular scope of municipal public works staff. Identifying a suitable maintenance plan and appropriate town staff to manage is critical for success. Rain gardens collecting large amounts of road runoff are prone to clogging without pretreatment. Space for settling particles, either in a catch basin sump or a forebay structure, is critical to avoid excess sediment buildup in the garden itself. Stormwater curb extensions, or curb bump outs, are landscaped areas that extend into the street and capture stormwater runoff. Conventional curb extensions, also known as bulb outs, chokers, and chicanes, are commonly used to increase pedestrian safety and help traffic calming. A stormwater curb extension shares these same elements, adding the benefit of stormwater management by allowing water to flow into the space for treatment through soil media and vegetation. This landscape space can be designed with the physical characteristics of vegetated swales, planters, or rain gardens, depending on the availability of space and specific site conditions. Stormwater curb extensions are particularly advantageous in retrofit situations because they can be added to existing streets with minimal disturbance and can simultaneously meet other municipal goals of safety and traffic calming. Where existing curb extensions are already in place, adding stormwater treatment benefits within the same space is possible by removing curb sections to allow water to flow through and modifying ground cover to allow water retention and infiltration. Curb extensions are excellent to use in steep slope conditions because they can act as a backstop for upstream flow. Existing residential streets offer some of the best opportunities for conversion of a portion of the street's parking zone into stormwater curb extensions. In Vermont, many low-density residential streets have unused on-street parking zones that could capture stormwater with no negative impact to residents. Stormwater curb extensions in low-density residential areas can often be installed with minimal impact to existing infrastructure. In some cases, the curb extensions can be designed so that the existing street curb and stormwater inlets remain intact. In areas where on-street parking is fully utilized, smaller stormwater curb extensions, spaced more frequently, can be used to minimize parking losses. In many urban examples, there are streets striped with no parking zones that could be converted into stormwater curb extensions without any loss of parking. Additionally, parking is generally not allowed within 20 feet of an intersection. These areas may be good candidates for stormwater curb extensions. Stormwater curb extensions have many active transportation, urban ecology, and neighborhood enhancement benefits. They can narrow intersection crossing distances, slow traffic, and create a safer and more walkable environment. They can provide additional stormwater storage and flow reduction, as well as pollutant filtration, which helps prevent damage to downstream water bodies. They can significantly help with placemaking and provide community public space. Stormwater curb extensions typically cost between $25 and $50 per square foot, depending on retrofit conditions or new construction, and if the stormwater curb extension has landscape side slopes or vertical planter walls. Common constraints with stormwater curb extensions include they sometimes require the removal of on-street parking. They can conflict with bike travel if adequate space is not allowed between the edges of curb extension and a street's travel lane. And finally, they can conflict with snow removal equipment maneuverability. Pervious paving systems allow rainwater to pass through their surface and soak into the underlying ground, reducing areas of imperviousness on a site and providing huge inlet areas to facilitate infiltration. There are generally three types of pervious paving options: concrete, asphalt, and pavers. Pervious concrete in its current mix formation has been determined to be ill-suited for cold climate application on driving surfaces due to Vermont's multiple freeze-thaw cycles and the deleterious effects of road salt application that cannot be eliminated from driving or parking surfaces as a result of vehicle tire tracking. On walkways, porous concrete can be effective if managed without salt or sand addition. Pervious asphalt is effective in Vermont's cold conditions, and several installations in the state have performed well over multiple years. The mix looks very similar to conventional asphalt, but has larger aggregate pieces and cures with pore spaces to allow water movement through the material. Permeable pavers come in a variety of materials and shapes. All use a sand and gravel mix between the pavers to provide permeability. The pavers themselves lack pore spaces. Reinforced grass and gravel grid systems also allow rainwater to soak into open pore spaces in the soil while providing a rigid driving surface for travel and vehicle parking. In areas needed for intermittent load-bearing use, such as overflow parking, grass paving or other paving planting hybrids can be used to provide structural support while allowing plant growth and stormwater infiltration. Pervious paving is primarily used on parking lots and roadways with low traffic speeds and volumes. Pervious paving should not be used in situations with known soil contamination or high groundwater tables, as the stormwater entering the subsurface could migrate pollutants. Pervious paving systems have many active transportation, urban ecology, and neighborhood enhancement benefits. They can reduce local flooding and icy conditions by allowing water to infiltrate rather than collect on the pavement surface. They can reduce the size of other stormwater treatment measures and provide additional perviousness within the urban context. They can significantly help with placemaking and provide community public space. Pervious paving systems typically cost between $15 and $30 per square foot, depending on the type of pervious paving material and the amount of gravel subbase needed. Common constraints with pervious paving include: requires well-drained native soil or underground gravel storage layers, needs special maintenance that may include new equipment purchases to keep pavement from clogging over time, has limited infiltration effectiveness on street slopes over 5%. Stormwater planters are narrow, flat-bottomed, often rectangular landscape areas used to treat stormwater runoff. They're a popular choice for urban environments. Their most distinguishing features are the vertical sidewalls that create greater storage volume in less space than a swale. Stormwater planters are easily incorporated into retrofit conditions and in places where space is limited, as they are highly versatile in shape and size. They can be built to fit between driveways, utilities, trees, and other existing site elements, and can be planted with a simple palette of sedges or rushes, or with a mixture of trees and shrubs. Because planters have no side slopes and are contained by vertical curbs, it is best to use plants that will grow at least as tall as the planter's walls to help soften the edges. Planters can be used in both relatively flat conditions and in steep conditions if they are appropriately terraced. Because they tend to have small footprints, they are best used to control small volumes of water and should not be installed where heavy runoff flows are likely. Stormwater planters are good candidates for main streets due to flexibility with siting and shape and a small footprint. They can fit between driveway curb cuts, utilities, trees, and street furnishings commonly found along urban streets. Planters can be a very good choice for streets that require on-street parking, but thoughtful design must accommodate pedestrian circulation. Planters can also be an effective design tool for parking lot applications. Parking lot planters can be designed to take the place of a few parking spots, or they can fit in the long, narrow space between the front ends of parking stalls. Due to their tidy architectural appearance, stormwater planters are an excellent choice to flank the front access doors to a commercial or retail location. Stormwater planters have many active transportation, urban ecology, and neighborhood enhancement benefits. They can provide separation between sidewalks and vehicular travel lanes, which help provide a safer and more walkable environment. Stormwater planters provide filtration and treatment of road and parking lot runoff, improving the quality of water flowing to downstream water bodies. They can moderately help with placemaking and provide community public space. Stormwater planters typically cost between $35 and $50 per square foot, depending on retrofit conditions or new construction. Common constraints with stormwater planters include planters are generally more expensive than swales due to the increased hardscape infrastructure. They are contextually appropriate in urban settings rather than in residential or rural communities, where stormwater planters may appear overbuilt or out of place. Because large, healthy trees provide a number of environmental and social benefits, ensuring they can thrive in downtown areas is a critical component of green streets. If given room to grow, trees can be a standalone stormwater system. Several innovative approaches to provide adequate soil quality and rooting space have emerged in recent years. Suspended pavements and structural soils give support to pavement while allowing roots to move through an extensive and loose soil profile. Suspended pavement systems utilize an underground scaffolding to support the weight of infrastructure without compacting soils. Engineered structural soils combine stone, soil, and a binding agent to hold the soil to the stones. This provides a similar service to suspended pavements without a rigid scaffolding. Structural soils support pavement while allowing tree roots to move through pore spaces. When there is interest in preserving existing trees in urban areas, suspended pavement, structural cells, and engineered soils can be used to create a bridge between a vegetated strip along the road and a green space. The bridge entails removing paving and compacted subbases in between the tree pit and the green space, and replacing the subbase with structural soil, and then repaving. Practices that allow for full maturation of a tree will see larger benefits over the long term than trees that are planted in areas that limit their growth. Designing sidewalks for the anticipated use will benefit street trees by increasing the potential rooting space underneath the surface. Urban street trees have many active transportation, urban ecology, and neighborhood enhancement benefits. They can provide a visual trigger to reduce traffic speeds in downtown areas, making a safer and more walkable environment. Trees provide shade, stormwater benefits through interception on leaves and evapotranspiration, and habitat for native species. They can moderately to significantly help with placemaking and provide community public space. Urban street trees typically cost between $150 to $600 per tree, depending on size and species. Total cost of tree depends on caliper and whether structural soil or suspended soils are used. It is common for structural soil to be used more now in urban environments, with a line item for the tree and a separate volume for structural soil. Common constraints with urban street trees include trees require regular, skilled maintenance to ensure long-term growth and health. Trees contribute leaf fall to street surfaces, increasing need for regular street sweeping efforts. Species selection is limited by above-ground infrastructure and utilities, making larger varieties ill-suited where overhanging power lines may conflict. Section 7 illustrates how the tools for green streets and parking lots covered in Section 6 can be applied to a variety of street and parking lot conditions throughout Vermont. Whether looking at residential, downtown commercial, or arterial streets, the stormwater tools can be applied to both new and retrofit conditions.
Thanks for watching. Next up, you will hear Becky Tharp lead you through Section 7, Green Street and Green Parking Lots examples.